Hello, my dear children. Welcome to the mathematics class. Today, we are going to discuss three-dimensional geometry. In this chapter, we are going to discuss the concepts of exercise 11.3. In the previous class, we have discussed the sums in the exercise 11.2. I hope you have learnt well the sums well. I hope you have understood the sums well in the exercise 11.2. Haven't you, my dear children? Right. Now come to this exercise 11.3. In this exercise, we are going to discuss about planes. Okay, my dear children. The first point. Plane. A plane is determined uniquely if any one of the following is known. Okay, my dear children. Here three cases are given. If any one of these three cases are given, we determine a plane. What is the first case? The normal to the plane and its distance from the origin is given. That is equation of a plane in the normal form. This is the first case to determine a plane. This is called equation of a plane in the normal form. In this case, normal to the plane will be given and its distance from the origin is also will be given. In that case, we write the equation of the plane. That is called equation of the plane in the normal form. Understood this point, my children? Right. Come to the second point. It is passes through the point. The plane is passes. The plane passes through a point and is perpendicular to a given direction. Okay, my children. The plane passes through a point and it is perpendicular to a given vector or given line. In that case, we find or we write the equation of the plane. Okay, my children, understood this point. Now come to the third point. When the plane passes through three given non-collinear points. In this case, we write the equation of the plane. This is the third case. We have to write the equation of a plane in these three cases. Okay, my children. Right. Understood these points, my children? Right. Now come to the second point. Equation of a plane in the normal form. In the beginning itself, in this point, we have discussed equation of a plane in normal form. Okay, my children. Here in this point, we are discussing equation of a plane in the normal form. Consider a plane whose perpendicular distance from the origin is d. Suppose observe this figure, my children. This is a plane. Okay, my children. In the space, it is a plane. It is at a distance of d units from the origin. Okay, my children. If you find the perpendicular distance from the origin to this plane is d units. Okay, my children. Understood this point? See the adjacent figure. If ON bar is a normal from the origin, here ON bar is a normal. Normal means it is a perpendicular from the origin. Okay, my children. So, modulus of ON bar is nothing but a small letter d. Understood this point, my children? ON bar is a perpendicular to the plane from the origin. That vector is a perpendicular to the plane from the origin to the plane, and n cap is a unit normal vector. You know, if it is a vector, we can find it's a unit vector. Okay, so n cap denotes a unit normal vector. Understood this point, my children? Right. Along ON bar, then ON bar is equal to d into n cap. Okay, my children, this ON bar, this vector can be written as d into n cap because the length of this vector is d and n cap is a unit vector along this ON bar. Okay, my children, let P be any point on the plane. Let P be any point on the plane. We are deriving the equation of the plane in the normal form. Okay, my children, this is the derivation. But in the examination point of view, this derivation is no needed. Directly we use the equation of the plane in the normal form. Okay, my children. Right. Therefore, NP bar, this NP bar is perpendicular to ON bar. Yes or no, my children? Because ON bar is normal to the plane, means ON bar is perpendicular to plane, and P is any point. So NP bar is perpendicular to ON bar. Okay, my children. So these two vectors are perpendicular to each other. We know that if two vectors are perpendicular to each other, then their dot product is 0. Therefore, NP bar dot ON bar is equal to 0. This is equation 1. Let us consider this result is equation 1. Understood this equation, my children? Right. Let R bar be the position vector of the point P. Let us consider the position vector of this point P is R bar. This is a variable point. Okay, my children. Then NP bar is equal to, how do you write NP bar in terms of position vectors? OP bar minus ON bar. Yes or no, my children? Do you remember this point? Yes, that is equal to OP bar. OP bar is nothing but position vector of the point P. That is R bar minus ON bar. We have written ON bar is equal to D into N cap. Understood this step, my children? Right. Therefore, equation 1. In this equation 1, let us substitute these values. NP bar. NP bar can be written as R bar minus D into N cap dot ON bar. ON bar is nothing but D into N cap is equal to 0. Understood this step, my children? Right. Now let us simplify this equation. Here D is a numerical coefficient. So let us divide this entire equation by D. Then what will you get? R bar minus D into N cap in dot N cap is equal to 0, because D is not equal to 0. D is a scalar. So we are dividing this entire equation by this scalar. Understood this step, my children? Right. This implies here we are using the distributive property. R bar dot N cap minus D into N cap dot N cap is equal to 0. By using the distributive property, we got this step. Understood this step, my children? Right. This implies R bar dot N cap, we write this first term as it is, minus D into N cap dot N cap. N cap dot N cap is nothing but N cap whole square. That is equal to modulus of N cap whole square. That's all, my children. N cap is nothing but unit vector. So the length of this unit vector is 1. So 1 whole square, that is equal to 1. Understood this point, my children? So D into 1, what will you get? D only. So we wrote the second term as D only. Understood the second term, my children? Right, is equal to 0. This implies from this equation we can write R bar dot N cap is equal to D. This is the vector form of the equation of a plane. This is called vector equation of the plane in the normal form. Remember this equation. Okay, my children? Now we write this equation in the Cartesian form. This is the vector form of the plane, vector equation of the plane in the normal form. We write the same equation, the equation of the plane in the Cartesian form. Okay, my children? So equation 2 gives the vector equation of the plane, where n cap is a unit vector normal to the plane. Okay, my children, we have taken like this only. N cap is a unit vector along the normal to the plane. Let P x comma y comma z, order triplet x comma y comma z be any point. Understood this point, my children? Right. On the plane, then OP bar is equal to R bar is equal to xi cap plus yj cap plus zk cap. Okay, my children, understood this step? Right. Let order triplet L comma M comma N be the direction cosines of n cap. Then n cap is equal to Li cap plus Mj cap plus Nk cap. Yes or no, my children? Can we write this unit vector like this or not? Right. Then equation 2 gives xi cap plus yj cap plus zk cap dot li cap plus mj cap plus nk cap is equal to D. Understood this step, my children? Right. That is, if you multiply these two vectors by dot product, scalar product, then what we get? Lx plus my plus nz is equal to d. Understood this step, my children? Right. This is the Cartesian equation of the plane in the normal form. This equation is said to be equation of the plane, Cartesian equation of the plane in the normal form. In this plane, x, y, z denotes any point on the plane. L, M, N denotes the direction cosines of the normal to the plane. Remember these points, my children. And here small letter d denotes the distance of the plane from the origin. Okay, my children. Understood these points? Right. Note, equation Lx plus My plus Nz is equal to D shows that if r bar dot ai cap plus bj cap plus ck cap is equal to D is the vector equation of a plane, then in the place of L, M, N, if you take A, B, C, that is the direction ratios, then what will get? Ax plus by plus cz is equal to D. Yes or no, my children? By dot product of these two vectors, we get this equation. Yes or no, my children? Right. Is the Cartesian equation of the plane where A, B and C are the direction ratios of the normal to the plane. In case the direction ratios of the normal to the plane is given and distance of the plane from the origin D is given, then the equation of the plane is ax plus by plus cz is equal to d. Remember these points, my children, as a formula. Okay, my children. Right. Note, if d is the distance from the origin and L, M, N are direction cosines of the normal to the plane through the origin, then the foot of the perpendicular is LD, MD, ND. Sometimes they will ask, find the foot of the perpendicular from the origin to the plane. In that case, use this formula LD plus LD, MD, ND, where D denotes the perpendicular distance of the origin, distance of the plane from the origin, and L, M, N denotes the direction cosines of the normal to the plane through the origin. Okay, my children, understood this point? Right. Now come to the next point, that is third point, equation of a plane perpendicular to a given vector and passing through a given point. Here we are deriving the equation of a plane which is perpendicular to a given vector and passing through a given point. Here also, just to I am explaining the derivation of this equation of the plane, but in the examination point of view they won't ask the derivation of this equation. Just we use this equation of the plane as a formula. Just to remember this equation as a formula. Okay, my children? Right. In the space, there can be many planes that are perpendicular to a given vector. Suppose this is a vector. In the space, there is a vector. So, for this vector, there are infinitely many planes which are perpendicular to this vector. That's all, my children. But through a given point P, x, y, z, only one such plane exists. See here, only one point is there. So perpendicular to this vector and passing through this point, there is only one plane exist in the space. Understood this point, my children? Right. Let a plane passes through a point A with the position vector r bar. Here A be a point in the plane. Okay, my children? And its position vector is a bar. And perpendicular to the vector n bar. So this is the plane perpendicular to vector n bar. This is n bar. This is the given vector n bar. Understood this point, my children? So for this vector n bar, this is a plane. In this plane, there is a point A with position vector a bar. Understood these points, my children? Right. Let r bar be the position vector of any point P x, y, z in the plane. To derive the equation of this plane, we are choosing any point in the plane P with the position vector r bar. Coordinates are x, y, z. Understood this point, my children? Then AP bar is perpendicular to N bar. Yes or no, my children? Then the point P lies in the plane if and only if AP bar is perpendicular to N bar. Yes or no, my children? This AP bar. If you take P anywhere on this plane, AP bar is perpendicular to this vector. Yes or no, my children? Right. That is AP bar dot N bar is equal to 0 because these two vectors are perpendicular to each other. So that is why the dot product of these two vectors is equal to 0. Understood this equation, my children? Right. But AP bar is equal to, how do you write this vector in terms of position vectors of the points A and P? Yes, OP bar minus OA bar. Yes or no, my children? Right. That is equal to OP bar. OP bar is nothing but position vector of the point P. That is R bar minus the OA bar denotes position vector of the point A. That is A bar. R bar minus A bar. Understood this point, my children? Right. Now we substitute R bar minus A bar in the equation AP bar dot N bar is equal to 0. Then we get R bar minus A bar dot N bar is equal to 0. Understood this equation, my children? This is the vector equation of the plane. Understood this point, my children? Right. Remember this equation as a formula when a plane is passing through a point and perpendicular to a given vector. Okay, my children? Right. Now we write this equation of this plane in the Cartesian form. Okay, my children? Right. Now let us write the Cartesian form of the plane. Okay, my children. Let the given point A be ordered triplet x1, y1, z1 and P be ordered triplet x, y, z and direction ratios of the vector n bar are capital letter A, B and C. Okay, my children. Then A bar is equal to, this can be written as xi cap plus yj cap plus zk cap. Yes or no, my children? X1 I cap plus Y1. X1 I cap plus Y1 J cap plus Z1 K cap. Now, R bar can be written as Xi cap plus Yj cap plus Zk cap. Yes or no, my children? And this vector N bar can be written as capital letter A I cap plus capital letter B J cap plus capital letter C K cap. Okay, my children? We wrote these 3 points in the vector form, in the component form. Okay, my children. Now, R bar minus A bar dot N bar is equal to 0. This is the vector form, the equation of the plane in the vector form. Now we are substituting R bar, A bar and N bar in this equation. R bar minus A bar, R bar minus A bar, what will get? X minus x1 into I cap plus Y minus y1 into J cap plus Z minus z1 into K cap dot N bar is equal to A I cap plus B J cap plus C K cap is equal to 0. Understood this step, my children? Right. This implies we are finding the dot product of these two vectors. Then what will you get? A into x minus x1 plus B into y minus y1 plus C into z minus z1 is equal to 0. This is the Cartesian form. Cartesian equation of the plane. When a plane is passing through a point x1, y1, z1 and perpendicular to a vector n bar. Okay, my children, whose direction ratios are A, B, R and C. Here capital letter A, capital letter B, capital letter C denotes the direction ratios of the normal to the plane. Remember this point, my children. Here x1, y1, z1 denotes the point in the plane. Okay, my children. Right. Now come to the next point, that is fourth point. Equation of a plane passing through 3 non-collinear points. Okay, my children, in the beginning of this exercise, we have discussed there are 3 cases to determine a plane. This is the third case. If 3 non-collinear points are given, there exists one and only one plane passing through 3 non-collinear points. Let R, S and T be 3 non-collinear points. on the plane with position vectors A bar, B bar and C bar respectively. Okay, my children, we have taken the position vectors of the point R, S and T are A bar, B bar and C bar respectively. Okay, my children, understood this point. The vectors RS bar and RT bar, these two vectors are lying in the same plane. RS bar and RT bar both lie in the same plane because all these 3 points in the plane. So RS bar and RT bar also lies in the same plane. Yes or no, my children? Right. Therefore, the vector RS bar cross RT bar is perpendicular to the plane containing the points R, S and T. Previously, we have discussed in the vector product of two vectors or cross product of two vectors. The cross product of two vectors is perpendicular to the both vectors A bar and B bar. So similarly here RS bar cross RT bar is a vector perpendicular to this plane. Understood this point, my children? Right. Let R bar be the position vector of any point P in the plane. Therefore, the equation of the plane passing through point R and perpendicular to the vector RS bar cross RT bar is RP bar dot RS bar cross RT bar is equal to 0 because RP bar and these two vectors perpendicular to each other. Therefore, the dot product of these two vectors is equal to 0. Understood this point, my children? Right. This implies RP bar can be written as OP bar minus OR bar. As so, my children, dot RS bar cross RT bar is equal to 0. Understood this step, my children? Right. This implies OP bar is nothing but R bar minus OR bar. Position vector of the point R bar. Position vector of the point R is A bar. Assignment children dot here also RS bar means OS bar minus OR bar cross RT bar means OT bar minus OR bar is equal to 0. Understood this statement, children? I wrote this vector and this vector in terms of position vectors of the points. Okay, my children? Right. This implies R bar minus A bar dot here OS bar position vector of the point S, that is B bar, minus OR bar position vector of the point R, that is A bar, cross position vector of the point T is C bar, minus position vector of the point R is A bar, is equal to 0. Understood this equation, my children? Right. This is the equation of the plane in vector form passing through three non-collinear points. Okay, my children. So remember this equation. This is the vector equation of the plane. Okay, my children. Which is passing through the given three non-collinear points. Now we write this equation in the Cartesian form. Okay, my children. Now come to this point, Cartesian form. Let x1, y1, z1, x2, y2, z2, and x3, y3, z3 be the coordinates of the points R, S, and T respectively. If you take the coordinates of the points R, S, T in terms of x, y, z coordinates. Okay, my children, let x, y, z be the coordinates of the any point P on the plane with the position vector R bar. Then RP bar is equal to x minus x1 into I cap plus y minus y1 into j cap plus z minus z1 into k cap. Okay, my children, understood this step. Similarly, RS bar is equal to x2 minus x1 into I cap plus y2 minus y1 into j cap plus z2 minus z1 into k cap. Okay, my children, understood this step. Similarly, RT bar is equal to x3 minus x1 into I cap plus y3 minus y1 into j cap plus z3 minus z1 into k cap. Understood this step, my children? Right. Substituting these values in the equation RP bar dot RS bar cross RT bar is equal to 0, we get determinant of the matrix of order 3. Okay, my children. In the first row, we get x minus x1, y minus y1, z minus z1. We write these three values in the first row. And these three numbers, we write in the second row. x2 minus x1, y2 minus y1, and z2 minus z1. Understood this is second row, my children. Similarly, in the third row, we write these three numbers. x3 minus x1, y3 minus y1, z3 minus z1, that is equal to 0. This is the equation of the plane in the Cartesian form, which is the equation of the plane in the Cartesian form passing through three non-collinear points x1, y1, z1, x2, y2, z2, and x3, y3, z3. Okay, my children. In the questions, these three non-collinear points will be given. Then they will ask you to write the equation of the plane in the Cartesian form. So it is passing through these three non-collinear points. Then you should remember this equation. Then you have to expand this determinant. You know how to expand the determinant of a matrix of order 3 by 3. That's what the children. So use that previous knowledge and expand this determinant. Then you get equation of the plane in the Cartesian form. Okay, my children. Understood? Right. Now come to the next point, that is a fifth point, intercept form of the equation of a plane. Okay, my children, this is another form of an equation of a plane. Let a plane makes intercepts A, B and C on X, Y and Z axis respectively. Then the equation of the plane is X by A plus Y by B plus Z by C is equal to 1. In the case of lines, you have learned the intercept form of a line. Similarly here we can write the equation of a plane in the intercept form. Suppose this is a plane. This plane is making intercepts A, B and C on X, Y and Z axis respectively. Then the equation of the plane is X by A plus Y by B plus Z by C is equal to 1. Okay, my children, remember this equation as a formula. Okay, my children. Right. Now come to the sixth point. Plane passing through the intersection of two given planes. In this point we discuss the equation of a plane passing through the intersection of two given planes. Okay, my children. Right. Let pi 1 and pi 2 be two planes with equations r bar dot n1 cap is equal to d1 and r bar dot n2 cap is equal to d2 respectively. This is the equation of the plane pi 1 and this is the equation of the plane pi 2. These two planes are intersecting here. Okay, my children. If two planes are intersecting, then we get a line of intersection, not point of intersection. Okay, my children. If two lines intersect, then we get point of intersection. Whereas if two planes are intersecting, then we get a line of intersection. Understood this point, my children? Right. The position vector of any point on the line of intersection must satisfy both the equation. Yes or no, my children? If any point is lying on this line of intersection, any point, then this point satisfies this plane equation and this plane equation. Yes or no, my children? This is a common part. That is why it satisfies both equations. If t bar be the position vector of a point on the line, then t bar dot n1 cap is equal to d1 and t bar dot n2 cap is equal to d2. Yes or no, my children? Right. From these two equations, we can derive d bar dot n1 cap plus delta n2 cap is equal to d1 plus lambda d2 for all the real values of lambda. This is the equation of the plane passing through the intersection of the two given planes. Okay, my children, understood this point? Right. Since t bar is arbitrary, it satisfies for any point on the plane. Okay, my children, understood this point? Hence, the equation r bar dot n1 bar plus lambda n2 bar is equal to d1 plus lambda d2 represents a plane P3, which is such that if any vector r bar satisfies both the equations pi 1 and pi 2, it also satisfies the equation pi 3. That is, any plane passing through the intersection of the planes r1 r bar dot n1 bar is equal to d1 and r bar dot n2 bar is equal to d2 has the equation r bar dot n1 bar plus lambda n2 bar is equal to d1 plus lambda d2. This is the vector equation of the plane which is passing through the intersection of two planes. R bar dot n1 bar is equal to d1 and r bar dot n2 bar is equal to d2. Okay, my children, understood this equation? Remember this equation as a formula. Memorize this equation. Now we write this equation in the Cartesian form. Okay, my children. In the Cartesian form, let n1 bar is equal to a1 I cap plus b2 j cap plus c1 k cap, and n2 bar is equal to a2 I cap plus b2 j cap plus c2 k cap, and r bar is equal to xi cap plus yj cap plus zk cap. Okay, my children. Then the equation 1, this equation becomes a1x plus b1y plus c1z minus d1 is plus lambda into a2x plus b2y plus c2z minus d2 is equal to 0. Remember this equation also, my children. This is a Cartesian form of a plane. Cartesian form of the equation of a plane which is passing through the point intersection of the planes a1x plus b1y plus c1 is equal to d1 and a2x plus b1y plus b2y plus c2z is equal to d2. Understood this point, my children? Right. Now come to the next point, that is the sixth point, coplanarity of two lines. In this point we discuss in which case when the two lines are said to be coplanar, when the two lines are said to be they are lying in the same plane. Okay, my children, the two lines r bar is equal to a1 bar plus lambda b1 bar and r bar is equal to a2 bar plus mu b2 bar are coplanar if and only if a2 bar minus a1 bar dot b1 bar cross b2 bar is equal to 0. If this condition is satisfied by these two lines, then the two lines are said to be coplanar. Understood this point, my children? Right. Suppose if the two lines are given in the Cartesian form like this, x minus x1 by a1 is equal to y minus y1 by b1 is equal to z minus z1 by c1. This is the equation of the first line in the Cartesian form, and this is the equation of the second line in the Cartesian form. X minus x2 by a2 is equal to y minus y2 by b2 is equal to z minus z2 by c2. Then these two lines are said to be coplanar if and only if determinant of x2 minus x1, y2 minus y1, z2 minus z1 in the first row, in the second row a1, b1, c1, and the third row a2, b2, c2. Then the determinant of this matrix is 0. Then these two lines are said to be coplanar. Understood this point, my children? Right. Now come to the next point. That is seventh point. Distance of a point from a plane. In this point we discuss the distance of a point from a plane. If the equation of the plane is r bar dot n bar is equal to d, where n bar is a normal to the plane, then the perpendicular distance of the point P with the position vector r bar is modulus of a bar dot n bar minus d by modulus of n bar. Remember this formula. Remember this point as a formula, my children. Memorize this point as a formula to find the distance of a point from the plane. Okay, my children? Right. Note, the length of the perpendicular from the origin to the plane r bar dot n bar is equal to d is modulus of d by modulus of n bar. This is also a formula. Remember this point also as a formula. Okay, my children. Suppose if the equation of the plane is given in the Cartesian form like this, then the distance of the point P x1 comma y1 comma z1 from the plane ax plus by plus cz is equal to d is modulus of ax1 plus by1 plus cz1 minus d whole divided by square root of a square plus b square plus c square. Okay, my children, remember these points as a formula. Memorize these points as formula, my children. These are very useful points to solve the sums in the exercise 11.3. Okay, my children. Right.